Well, here's the little screencast related to RC circuits that I mentioned. And in this one, I'd like to go over really 6 kinds of questions. And they're outlined here on the screen that you see. There's really 2 different ways we can look at an RC circuit. The first one I'll show you is when we need to charge a capacitor. And the second is when we need to discharge a capacitor. Now, the AP folks really love to ask questions like, what happens immediately after you close a switch, or a long time after the switch has been closed? Because the more time-consuming, I guess, mathematical parts are the ones in between. What about some time in between immediately after closing and a long time later? So we'll kind of deal with those all at once when I show you the 2 different kinds of circuits. So I'll start with the charging kind of circuit. And a typical circuit diagram is shown here at the top. And it's, in the simplest case, just some source of voltage. They call it in this diagram V sub S. It might just be called V, or the voltage of the battery, or something like that. But in our examples, we're going to be using some constant voltage source, such as a typical battery. And then we usually include a switch just to make it easier to describe, when we start the clock. Because as I mentioned before, this is a very critical when we talk about time, that you know when the time starts. So in a charging capacitor, when we first start the clock is typically when we close the switch. So you could think of it as completing the circuit as I did there. And then we have a resistor and a capacitor. And in the more advanced cases, we might have multiple branches with different resistors or capacitors. So if you just think about what's going to happen if the capacitor starts out empty and we now have a battery hooked up to it, then we're going to start pumping charges off of one plate of the capacitor and onto the other, which is going to mean that current is flowing. Now, real charges are moving from the top plate to the bottom plate, but we always speak of conventional current, which is the current flowing, in this example here, clockwise, as though the positive charges are moving from the bottom plate to the top plate. Well, now we can see that if we include a resistor in here, that's going to provide some resistance to the flow of electricity. And so that's why we have to include it in our analysis. Now, if we start out with a capacitor completely empty, then that is when it's going to be easiest to fill the capacitor up. And as the capacitor gets more and more full, it gets more and more difficult to pack more charges on there. So what I'm going to do here is describe the math of figuring out just how much charge has built up on the capacitor, and that's going to also lead us to figuring out how much current is flowing at any one time. Now, the equation I'm going to use here is going to start out as what we call a Kirchhoff's loop equation. And that's where you start at some point on the diagram, and I'm going to use the lower left-hand corner here. And I'm going to go around that circuit. I like to go clockwise around a circuit. And I'm just going to write an expression for every jump or drop in potential that I experience. So maybe I'll do this in red here. So what do we get when we first start up the left side of that circuit? Well, we're going from minus to plus across that battery. And so we will have an increase of V sub S. And then the switch does nothing because it's basically just a wire. And then we're going to have to go across a resistor in the direction that current is flowing. And so that always provides a drop of voltage equal to I times R. Now, I is going to be different at different points in the time, but R is going to be constant. So we'll just remember that I is really a variable in this case, and R is just a parameter. And then we're going to go from the plus end of the capacitor across to the minus end, and that's going to be a drop as well. Well, the amount of drop of potential across a capacitor depends on how much charge has built up across that capacitor. You might remember the QVC equation, and so Q here again is a variable that changes with time, and C is a parameter that is just a constant in this problem. So both of those are the minuses, and then we're back to where we started here in the lower left-hand corner. So that means we've traversed the entire circuit, and all those jumps and drops have to have added up to be 0. So now what we've got here is 3 parameters, the V sub S, the R, and the C, and 2 variables, I and Q. But here's what's important. those two variables are related to each other. In fact, one is literally the definition or defined in terms of the other. I is described as dq dt using the calculus kind of a notation. So what happens if we rewrite this substituting dq dt in place of I? Well, I think I'm going to rewrite this here while I pause this, and then you could do it yourself if you wish, and we'll see what we get. So here's this equation rewritten with that substitution. And notice what we have here is a form of an equation. We've not seen this often before, although I mentioned it back in the mechanics unit. It's known as a differential equation because it involves a variable Q. In this case, Q is how much charge has built up on the capacitor, and that changes with time. We also have the time derivative of that in the equation, dq dt. That's what we substituted in for current. So you don't do algebra on these, you actually recognize the solution to a differential equation and you write the form. You will not be expected to necessarily do all differential equations, although this is one that you'll eventually learn to do if you don't know how to do it already via separation of variables. But for the purposes of this video, I am simply going to write the solution. That is, exactly how does Q change with time? And here's how that looks. So here is that function for Q, what we call the solution to the differential equation. And it is in the form that is known as an exponential approach. And I'll show you why when I show you the graph that looks like this. Now we could also write an equation for I, because if we just take the derivative of this function with respect to t, we will get I. Now that's not the worst derivative you've ever had to do, but I'm going to go ahead and do it for you just to keep this moving. And there is that derivative. It might be a good exercise if you want to just practice your calculus a little bit to prove to yourself that Q of t is actually a proper solution to that equation above, and that I of t is indeed the derivative of Q of t. You can trust me on this, and you can find these equations pretty much anywhere, including your textbook, or some form similar to it. But it's still something that you ought to be able to verify for yourself. So this is how you answer questions that say, for example, at a particular time t, what is the charge on the capacitor, or how much current is flowing through the circuit. You literally plug in your parameters, V, R, and C, and then you plug in whatever time you're asked about. And if we do it graphically, now I'm going to show you what we have graphically, because what I've got is some graphs of the voltages and the current that we would measure. And so I want to show you why we ask questions like immediately after the switch is closed or a long time after. And one thing you can recognize here are the shapes known as the exponential decay and the exponential approach. The ones that decay to zero go down, and the one that approaches a higher value is known as the exponential approach. Now, the one on the marked V sub C, that represents the voltage that we would measure across the capacitor. And it follows this same kind of exponential approach that the charge does, and that's because the voltage on a capacitor is directly related to how much charge is on it. So if we look at what happens immediately after the switch is closed on a charging circuit, here is the voltage on the capacitor right here, and that is 0, and that's because we don't have any charge on there yet. And a long time after that, we eventually reach a value equal to the battery's voltage, what we call V sub S in this example. So very immediately after, it's 0, and a long time after, it's the voltage of the source. And the resistance does just the opposite. The voltage across the resistor starts out at the same as the battery's voltage, that's up here, and it ends up at 0, because after a long time we're going to have moved all the charge that we're able to with this battery, and so there won't be any current left, and that's why it decays to 0. The graph on the right here, maybe I'll outline that in green, that shows what happens to the current. And as I mentioned before, because we start out with no charge on the capacitor, that means we can move current as rapidly as we're ever going to be able to. So there's its starting point, and in that circuit it's just the battery's voltage divided by the resistance, that's I equals V over R. But after a long time, because the capacitor ends up filled and can't move anything else, then the current has to stop as well. So those circle points there are your initial and your long time after kinds of quantities, and then everything in between you're going to have to use an equation that has either the exponential approach or the exponential decay form. So there's your charging circuit. Now let's take a look at a discharging circuit. So what you can't tell in the picture here is that in a discharging circuit, we start with a filled capacitor. So it doesn't really matter whether the top plate's plus or minus. If we use this as maybe the same capacitor we had in the last example, then we would have put a bunch of positive charge on the top plate and a bunch of negative charge on the bottom. What we've done here is we've taken out the source voltage. And we usually do that, and I'll show you in a few minutes just how we make a circuit that does that very easily. But we just imagine now we still have the resistor hooked up, but now it is just between the plates of the capacitor. Not a bad idea here to maybe imagine there's a little switch that is open at the very beginning. That way we can close it and call that time 0, and that's when charge starts to flow again. Now if you think just on a descriptive level here, that capacitor is not going to remain charged like that unless the battery is still hooked up to it, kind of holding them on there. So as soon as we throw that switch down, the negative charges are going to start to move back to the other plate so that we neutralize it, and therefore we're going to get current flowing again. And we're going to get the most current at the beginning because that's when the charge is going to be most pushed away from the other charges on the plate. And then eventually we will have emptied the capacitor, we'll have neutralized both plates, and we will be down to 0. So that's why we can see on a graph here that the voltage across the capacitor starts out at its maximum at the very beginning when it's fully charged, and eventually we'll get down to 0 again. They don't show it reaching 0, but there's a little asymptote there. And what this doesn't show, and I'll just do a quick sketch here, is what happens to the current in that circuit. And that's easy to show because the current does exactly what the charge on the capacitor is. So I'll actually draw the current here in blue, and it follows the same kind of shape. So I'll just mark that I and how it changes with T. Because remember, it's as the charge leaves the capacitor, it's also that is what we're talking about when we say the current. So they will stop eventually once the capacitor's empty of charge, lost all its voltage. We have also stopped all the current flow. So there's nothing that really exponentially approaches on a discharging circuit. Everything decays. That would be the capacitor's voltage, the potential difference across the resistor, that would be the current, and so that's just a nice characteristic of a discharging circuit. Now while we're here, I want to point something out that we could have pointed out on the last screen too, and that's this 37% number. Turns out, because of the nature of the differential equation, and I'll show you what I mean by the nature of it, they all have something like this term, negative t over RC. That's an exponent of E. Sometimes it's 1 minus that, sometimes it's just that. But that tells you something kind of curious here. RC actually has the same units as T. They have to be in a fraction like that in an exponent. So RC is known as the time constant. It's sometimes labeled with the Greek letter tau, and it was on the last screen if you want to go back there a few minutes and look. But that's special because when the time is equal to RC, then this whole fraction here that I'll circle is equal to 1. So we have e to the negative 1. Well, e to the negative 1 is just a number that you get used to when you're doing these charging and discharging circuits. E to the negative 1 is 0.37. So what that means is, after one time constant's worth of time, we have decayed to 37% or 0.37 of our starting value. Whether that's the voltage on the capacitor or the starting current or whatever, we're at 37%, which also means we've lost 63% of the initial value. So that's why that 37% is marked on there. If we have another time constant that goes by, maybe right about here on our graph, this would be like 2 RCs, then we would have lost yet another 37% of what we were at before. So this little amount in here, we're left with 37% of where we were of 37%. So you can kind of see that's where we get the exponential decay. Let me bring those other two graphs up and I'll show you real quick how we look at that on an exponential approach graph. So here's those two graphs showing the voltage that built up on the capacitor for the charging circuit. This is not the discharge circuit. And this was the decaying voltage across the resistor as it built up across the capacitor. And we see here, now the time constant is marked with tau. So this is one time constant's worth of time. And here's those magic points. At that particular time, we have lost 63% of our resistor's voltage, so we are at 0.37 of the initial value, but we have built up to 63% of the capacitor's final voltage. Remember, this was going to be the voltage of the battery, or V sub S as it was called in that figure. So that's what's special about one time constant. And if we go another time constant over, then, and I didn't do the math here, but losing another 30% of, or 37% of what we were at gets you to about here. That looks to be about maybe between 15, roughly 15%. And we've built up to about this point for our capacitor's voltage. That looks to be almost 80%. And so here's kind of a special point too. If you notice at 5 time constants, you almost can't tell that it's not on 0 yet. And up here, it looks like we're just about flat. And that's kind of a rule of thumb that after 5 time constants, you are at 99% of your final capacitor voltage, and you've lost 99% of your resistor's potential difference. So for all intents and purposes, you can say that we've just about reached our final values, even though technically we have asymptotes here. So that's where those two special numbers come from. It's not uncommon at all to see those floating around in different problems. So I think I'm going to end it here, and more clarification, of course, love to talk to you in the classroom, maybe replay part of this and look for some supplementary materials if that helps. And hopefully you got a good little start here on the RC circuits.